What we're going to look at now in this video is a different measure of dispersion. We're going to look at the variance and the standard deviation. Again, these measurements tell us about how spread out the data set is. The variance, by definition, is the arithmetic average of the squared difference between each data value and the mean of the data set. Well, if that isn't a mouthful, I don't know what is. Okay. Furthermore, let me just give you the formula for this. The variance, which we use the symbol sigma squared. Okay, here's the formula. x1 minus the mean squared plus x2 minus the mean squared plus x3 minus the mean squared. And we continue doing this for our total number of data values, and then we divide by n. Okay, well, I think the formula is almost worse than the definition. But let's talk about the definition and the formula and what it's really getting at. And then we'll look at an example of finding variance and standard deviation. First of all, you have to take a step back from this big nasty formula and from this long definition. Focus on the first thing. It's the arithmetic average. You've heard this term before. Arithmetic average simply refers to the mean. The mean is calculated by adding up a bunch of things and dividing by how many there are. Take a step back from the big nasty formula for a minute and look at what's really going on. We are simply adding up a bunch of things, and then we're going to divide by how many of those things there are. Okay. Now, what is it that we're adding up? Because these expressions that we're adding up that I've underlined in blue in the numerator are a lot more complicated than, say, these simple data values down here for class 1. So if we look at what exactly it is, what these expressions are that we're adding up, x1 minus the mean, what is that talking about? Well, remember that the mean of this data set was 71. Okay? What we're really interested in with the variance is looking at how far each data value lives from the mean. So 75 is 4 away from the mean. 73 is 2 away from the mean. Think about how I figured out that this was 2 away. I took 73 minus 71. So that's exactly what we're doing up here when we're saying take the data value and subtract the mean. What we're looking for is how far does each data value live from the mean. So we look at every single data value and how far it lives from the mean. And in order to do that, we take each data value and subtract it from the mean. Now consider this. A data value like 75 is 4 away from the mean. 75 minus 71 is 4. Look at a data value of 67. 67 is also 4 away from the mean. But when we subtract 67 minus 71, we get a negative. The sole purpose of that negative is to indicate direction. It indicates that this data value of 67 is below the mean. Statistically speaking, when we're dealing with measures of dispersion, we don't care about direction. That means a data value like 75 and a data value like 67 are exactly in the same boat. They're both 4 away from the mean. So we don't care what direction you are from the mean. All we care is that you're not at the mean. Well, how can we eliminate direction then if we're not interested in it? Consider what happens when you square a negative number. It becomes positive. Of course, squaring a positive number makes it positive as well. This action of squaring is what removes the direction. So by squaring a negative difference, it becomes positive. We've in essence removed direction. Well, if we're going to square the negatives, we square the positives as well, because even though we don't write the positive 4, it is still carrying a direction. So back up to the formula, what are we adding up? We're adding up how far each data value lives from the mean, and the reason we're squaring it is to remove direction. Now, why is it that we have to add all these up and divide by how many there are? Well, consider this. If I wanted to compare two classes, let's say I wanted to compare two sections of my 120 and how they did on their first exam. It certainly wouldn't make sense to randomly select one student from each class and use that as my comparison, because the student that I select from each class may or may not be representative of the class as a whole. It could be that the person I randomly selected from the first class did a lot better than the other people in the class, or it could be that they performed a lot worse. Maybe I get lucky and they performed about as well as everybody else, but there's no way to know. Same thing with the other class. If I just randomly select one person, they may or may not be reflective of the rest of the class. So what would be a better comparison? A better comparison of the two classes would be an overall average of the two classes' performances and compare those numbers. So if I wanted to compare two sections of my Math 120, what I might do is look at the mean for one class, the mean for the other, and base my comparison on that. Well, the same is true when we look at measures of dispersion. If I just randomly select one value from class 1, that difference may or may not be reflective of the entire data set. Class 2 would show an even bigger disparity. What if the data value that I randomly selected was this highest one? Well, that data value lives 23 above the mean. But if the one I randomly selected was this one, it's only 3 away. So getting this as my random selection and saying that that's reflective of the data set makes it look like the data set is very spread out. But picking this one as my random makes it look like the data set is not spread out. In order to get a more accurate picture or something that is reflective, we will take all of these differences and add them up and divide by how many there are. An average is more reflective of the entire data set than just one piece of data alone. What we're going to look at now then is an example of calculating the variance, and we'll do it by hand. So let's take a look at just a small data set. We're going to find the variance for a small data set of 5, 7, 7, 8, 10, 11. Now, in order to find the variance, and if we do it by hand, there's a lot of things that are involved. I need each data value, and I need the mean, because what I'm interested in is how far does each data value live from the mean. Furthermore, after I find that difference, I'm going to square it because I am not interested in direction. So I'm going to go ahead and I'm going to list out all of my data values here. In order to begin the variance calculation, I need the mean of the data set. Just to refresh, to find a mean, we add up all the data values and divide by how many there are. So in the numerator, we get a total of, I believe, 48. And when we divide by 6, we find the mean to be 8. All right, now we're ready to begin looking at how far each data value lives from the mean. The first data value of 5 is 3 below the mean. We get that by taking 5 minus 8. It comes out as a negative 3, but we're going to square that difference because we're not interested in direction. The next data value, if we find the difference, it's negative 1, and that's because 7 is 1 below the mean. But again, we square the difference because we're not interested in direction. The next data value of 7 is also 1 below the mean, but we square. The fourth data value is actually at the mean. The difference is 0. We square it in theory, even though 0 squared is 0. We square it to remove that direction. 10 minus 8 gives us positive 2. That makes sense that it's positive because 10 is 2 above the mean, so we should get a positive. But direction is still implied, so we need to square it to remove direction. Finally, 11 is 3 above the mean. It's a positive 3. We will square it to remove direction. Now remember, we said any one of these squared differences alone may or may not be reflective of the whole data set. So the best thing to do is take an average. So we will take and add up all of these squared differences and then divide by how many there are. Now, how many do I need to divide by? 6. There were 6 different squared differences in that final column. I understand that 0 does not add anything to the value of the numerator. And while it would be okay to leave it off in your addition, when you're adding up all those squared differences, it would be okay to leave it off the numerator. You have to count it as one of the data values, and so it comes into play in the denominator. If we didn't count it, then we would be saying that every data value that lives at the mean is excluded. and that would not be right. So when we add up all of those squared differences, we get 24, and 24 divided by 6 is 4. So sigma squared, which stands for our variance, in this case is 4. Now, unfortunately, it is not the variance that we work with. It's something called the standard deviation. Okay, well, at this point, you might be ready to throw something at me if I was standing in front of you, because you might be wondering why I made you go through all that big, long, nasty calculation if we don't even use the variance. Well, here's why. The standard deviation is simply the square root of the variance. So that means in order to get the standard deviation, you have to find the variance, and then you just square root it. If the variance is denoted as sigma squared, when we square root that, we get sigma. Sigma is the symbol for the standard deviation. So in our particular example, if I wanted the standard deviation of sigma, I go ahead and square root the variance. Remember, the variance was 4. So the square root of 4 is 2, and I find my standard deviation. The standard deviation is what we're going to use. Okay. So in class, we will be doing some examples of finding standard deviation by hand, variance and standard deviation by hand. I will also show you how to do it on your calculator. We'll do some practice problems, and then we will be talking about some different distributions.